So I leave the floor to my colleague, Dr. Andrea Vogliardi, and please.
Hello everyone, I'm Andrea Vogliardi. I'll be the chair for the next presentation, hosted by Professor Nicholas Karpowicz, who will talk about nonlinear optics in attosecond physics. Professor Karpowicz, you can just upload your slide and share your slides. Until you do it, I will present something about his research. Professor Karpowicz is a permanent scientist at the Max Planck Institute of Quantum Optics in Garching, Germany, where he also coordinates projects within the Ferenc Krausz group and co-lead the International Max Planck Research School for Advanced Photon Science. He got his Ph.D. in physics in 2009, working on terahertz gas photonics. Before his current position, he was a senior scientist here in Italy at CNR NANOTEC, and earlier a postdoctoral researcher and group leader at the MPQ. His main research focuses on the direct sampling of ultrabroadband spatiotemporal waveforms and on light-matter interaction in the strong field and attosecond regime, combining experiments with theory and numerical methods in nonlinear optics and quantum mechanics. Please, Professor Karpowicz, the stage is yours, and enjoy the session.
Thank you very much for the kind introduction and for the invitation to talk to you all. Yeah, so I'm going to talk about what we've been doing lately in my lab, focusing on the nonlinear optics code that I've open sourced in recent years, but going into first a little bit of the motivation of why I would do all of this programming. So first I'll talk a little bit about the science that we do, because I guess a lot of you aren't in the attosecond field. So I'll give a little bit of background on that, what we're interested in, what our motivations are, and then I'll get a bit into the code. All right, so I'm at the Max Planck Institute for Quantum Optics in Garching. So I'm working with Ferenc Krausz. He's the director of our division. So this was a couple of years ago in 2003. He won the Nobel Prize for all of this stuff. And so this is some of the people in my group here on the day that it was announced. We just sort of randomly took whatever glasses could hold some prosecco out of the cafeteria there, and I'll show some results from two of the students here. This is Emily Heinzerling, and this is Marco Dassi. Marco, by the way, is a graduate of the University of Padua. He's a Ph.D. student with me now. And if you want to find out more about what we do, our website is attoworld.de. So because all of this stuff is now on this Nobel website, they made some nice graphics that I can just steal. So just to give you an overview of the sort of traditional attosecond physics, it tended to be based around high harmonic generation in gases. So the high harmonic generation process, just to give you a little picture of it, it was you take an atom, typically a noble gas atom, you use a strong laser field to tear an electron off of this atom. You photoionize it with a tunneling process, and this electron that you've released now gets accelerated in the laser field. So it accelerates away from the parent ion, and then the laser field is going to accelerate it back. And if it comes back, it has a probability of recombining with the parent ion, but it recombines with some excess energy, which it has to release in the form of a photon. The nice thing about this process is that everything is coherent. Everything is locked in time to the laser field, which is driving the process, which means that this emission of these fairly high energy photons are very confined in time, because this tunneling process is very nonlinear. It only happens near the peak of the laser field, and this recombination happens with a certain timing, which is associated with the cycle of the optical field later. So we know when these photons are going to come out. They come out in one burst in the form of an attosecond pulse. So if you're not familiar with the timescales, an attosecond is 10 to the minus 18 seconds, so smaller than a femtosecond. And this process has been kind of the bread and butter of attosecond physics since about 2000 or so. And a lot of experiments have been using these high energy photons for time resolved spectroscopy and things like that. My part of the group has been doing things a little bit differently. So we do what we call field resolved attosecond spectroscopy, or attosecond measurements in general. And here we use the fact that because we have these attosecond pulses or other attosecond processes, like I'll show some results in a bit, we can actually measure the electric field of light. So this was the first time that we were really taking this seriously. This was actually some years ago now, where the measurement process that we were using was called attosecond streaking. So I don't want to go into all of the details of this, but it's just an application of these attosecond pulses that we made. And you can use these attosecond pulses to read the electric field of light encoded in a momentum shift of an electron that you measure with just some time of flight spectrometer. Now we started using this as a way of just saying, okay, we can measure the electric field of light. What information does this contain? So we know from Maxwell's equations that changes in the electromagnetic wave can be induced by the presence of a localized current inside of a material. So if there's some sort of nonlinear light matter interaction going on, the motion of charge carriers that we might induce inside of material, of course, has to be reflected in changes in the electromagnetic field. And then we thought, well, if we can measure changes in the electromagnetic field, can we go back and actually get a time domain picture of the motion of the carriers that were inducing all of these changes? So this was kind of a simple example of this in this was just a quartz plate. And we can send our light pulse through this plate at a high and a low intensity and look at how the waveform changes. So in this case, the waveform that's showing green was passing through the sample at low intensity. The pulse that you see in red was passing through at high intensity. And you see in the low intensity region of this pulse before the main peak, there's not much difference in the waveform. But in the high intensity region, there's a temporal shift. And this temporal shift is dominated mostly by the optical Kerr effect. So the light is changing the refractive index of the medium. This leads to a phase shift, and we see this encoded in the electric field here. So there's not too much exciting in that. It's just the Kerr effect causes a refractive index change, which causes the phase to change. But by taking this process a little bit more seriously, putting it inside of the nonlinear wave equation, which I'll focus a little bit more on in a few slides once I start talking about nonlinear optic simulations, we can just take the equations that we use for nonlinear light propagation and rearrange them such that we take two things that are our observables, so two electric fields, and we can express this as a change in electric field. I do a Fourier transform here to put it in the frequency domain. But this change in electric field, I can now say, well, I can get the nonlinear polarization out of this. So the nonlinear polarization that was going on inside of the medium is now an experimental observable. And using this nonlinear polarization as an experimental observable combined with the fact that the electric field is an observable, we can write an equation in this form, which is the energy exchange between the light field and the material, which just depends on two things. So the electric field that was driving the whole thing and the time derivative of the nonlinear polarization. And the time derivative of a polarization is just current. So this is just saying that field times current is power, or power density. And so we can actually track as our light pulse goes inside of the medium. It wasn't actually just doing Kerr effect, it was exciting carriers inside of the material, and we can actually see the absorption process happening in real time inside of the medium. So cycle by cycle or even sub-cycle, we can see how energy is going into and actually coming back out of the medium as the field and the electrons interact with one another. And we thought that this stuff was pretty cool. And really the limits to it were, well, what is our time resolution and what is our signal to noise ratio? And we've been working on making these things better. And a lot of it just comes down to getting shorter, more broadband optical pulses. So this is one of our more recent results. So this was basically Amelie's PhD thesis, and the paper came out a few months ago. Well, now more than a few months ago in March. And so we're using soliton dynamics in hollow core fibers to get very short pulses, but also to measure the electric field of these pulses. The first simulations on this were done by our collaborator, Francesco Tani, who is at the Max Planck Institute for the Science of Light in Erlangen. He's now moved to University of Lille in France. And what you see here is our pulse sort of propagating inside of this fiber. By soliton, we just mean that there is a compensation of a nonlinear phase by the linear phase inside of the fiber. This is all controllable through the geometry of the fiber, the pressure of the gas. In this case, we were starting with a pulse that was already fairly short. We let it go through the fiber, it gets even shorter. And just how much shorter was quite difficult to measure. So we have to detect the electric field of this waveform. And we have to actually keep it short after the fiber. So all of this was happening inside of a chamber, which is in vacuum. Inside the fiber, it was 10 bar of helium. So 10 bar of helium inside of a vacuum chamber is sort of a difficult situation, but Emily managed to do all these measurements. And this is what she saw in the end, that we have this electric field coming out of the fiber, which in its own right is an attosecond pulse, but it's an attosecond pulse made in a different way than the traditional high harmonic generation process that I was talking about before. We get a pulse with an attosecond duration. So we take this electric field, you square it, get the intensity, and in this case is say around 400 attoseconds, so less than a femtosecond, in good agreement with the simulations. But this attosecond pulse is now in the mostly in the visible spectral range, some content in the near infrared, some in the ultraviolet because it's very broadband. But it's in this nice range where there are a lot of interesting interactions that we can look at. So it gives us a chance to do attosecond physics in a very different photon energy range, which for a lot of things will be interesting. And we can also isolate, say, an ultraviolet pulse using the right reflective stuff. I just wanted to mention a bit about what Marco is working on, since he's one of your alumni. So he's using the same process in a bit more optimized setup, using just a single hollow core fiber for this. There are some experiments that he's actually doing with the pulses that come out of this that I don't have time to go into, but he also sees the same kind of thing. He gets even a shorter optical pulse coming out, and he's also done some tests of sort of long-term reproducibility of these waveforms, since if we were looking for information that's encoded in changes in the waveform, they should be stable on their own, and it seems that they are. So that's sort of our light source development that's going on, and you can see we're using nonlinear optics for all of this. The soliton dynamics are nonlinear optics. all of our lasers, in order to get very short pulses coming out, we use nonlinear process on top of nonlinear process on top of nonlinear process. And all of these things get complicated once you start cascading them together. And in order to make some predictions about how these systems that we're trying to build in order to do these experiments are going to work, we end up doing a lot of simulations of nonlinear optics. So that's what brings me to the nonlinear optics code that I wrote, which I call Lightwave Explorer. And the idea was to, instead of for each experiment, write a bit of code to try to simulate just that experiment, to build up a base of code that we trust for one type of nonlinear optics experiment and reuse as much as we can in order to simulate everything else that we do, such that we're kind of constantly revalidating the simulations that we do when we try something new. And when we introduce a new crystal, we can check, okay, are these parameters that I found in literature consistent with the other parameters that I found in literature? And then once we do that, then we can keep using this crystal. So it's a way of allowing us to build up our knowledge in a consistent way of how to make predictions of how these systems are going to interact. And then by opening it up to the rest of the community, it allows, well, one, it makes friends, and it also gets us some feedback. So I know of people at Imperial College in London and Princeton and the Max Born Institute that are using my code. And I'm not saying this to brag. I know this because they've all given me bug reports. And so I've found this actually quite a nice process. So the code itself is, I can talk a little bit more about that later. It's written in C++. And I do that because, well, in order to interact with GPUs on a fairly low level, that was just the way to do it. And I tried to set it up in such a way that there is a lot of visual feedback. And if you want to download it, actually, if you're on Linux, it's quite easy. It's on FlatHub. For the other platforms, if you go to the GitHub site, there's a QR code here, or it's just GitHub, my name /Lightwave Explorer, and there I have download of the Windows version. The Mac version you have to compile yourself for reasons I'll talk about in a bit. All right, so yeah, so a bit about why. In ultrafast optics, we use these nonlinear processes a lot, and they can be quite complicated, and sometimes we want to look inside and see what was going on. So this is just an example from a couple of years ago. This was a pulse compressing itself inside of a titanium dioxide plate, so a 2-micron pulse. And this is a process that we end up using a lot now in our lab. A lot of our laser sources are based on this nonlinear broadening inside of this titanium dioxide plate. And we wanted to look at, okay, how are things actually happening? And all of these complicated filamentation dynamics we could simulate and actually check versus what we can observe experimentally, like the pulse duration and the spectra that come out. But yeah, doing this consistently again across different experiments, again, this hadn't been a priority before, and I thought, okay, let's make this doable. And reproducibility is actually one of our goals now. So the hope is that when we publish something like this and we say, we could do this simulation and it agrees really well with the measurement, people can actually check that you can download my code, you can run the simulation, and then you say, okay, I have a slightly different laser source. How is this going to work for me? And use the same simulation and see how it's going to respond to parameters. So I think this is going away a bit from the traditional way that this was done, where you publish a paper and now you're done. You say, okay, my experiment and my simulation agreed with each other. If you disagree with that, well, we'll talk at some conference once and then forget about it. It's like, no, now you can actually download my code, you can run it, and then we can look more in detail about what any differences might be. So before I get into the coding, just a little bit about how it works. So it's a numerical simulation. So in the end, we're probably solving some partial differential equation, right? Here, there are two ways of doing it within my code, which it's going to depend on what kind of situation you want to actually solve. In nonlinear optics, there are just two main ways of doing this. One is what's called the unidirectional pulse propagation equation, where you make a bit of an assumption. You assume that the light is propagating forward in one direction. This allows you to take your wave equation and just express it as a first order equation in position of how your electric field, which can be a function of space and time or space and frequency, how this pulse, let's say, is going to evolve as it propagates through the material. The main driving term here is this nonlinear polarization. This is hiding a lot of the complexity of the simulation because there are a lot of tensors and things that go on and calculating this thing. But this is the basic equation that's responsible for it. So we're just looking at how our electric field changes as it interacts with our nonlinear medium. If the approximations that are in this unidirectional pulse propagation equation break down, then we can also solve in a more general way, which are finite difference time domain. So solving Maxwell's equations on a grid. This is numerically a bit heavier, but it's still not that bad. The main thing that's going to happen is if you're solving the interaction with a large material, say you have a thick crystal, the unidirectional pulse propagation, the memory footprint of this thing is going to scale with the length of the crystal, or the amount of work that you have to do is going to scale with the length of the crystal. The amount of work that you have to do in FTTD is going to scale with the square of the length of the crystal, because you have to hold the whole thing in memory and then propagate it through. If you're interested in more of the details about how I calculate all of these individual terms, there's a little paper about it there. And then let's talk about some of the programming challenges. So like I said, it's written in C++. I wanted it to run on GPUs in order to be fast, because I could see right away that some of these things that we have to solve are pretty heavy if you want to really do everything in full detail. The problem is there isn't a perfect framework for this. CUDA is proprietary to NVIDIA. If you want to use other GPUs, the main thing to use is SYCL, but the SYCL compilers, I have to say, are not very mature, and the runtime has some issues. Another thing you might use is Vulkan. Vulkan is sort of not nice to program inside. It's quite limiting how expressive the shader languages are, and Metal is like Vulkan but worse and only runs on Apple. The solution that I have so far is to use an abstraction called a functor in C++, and I'll show you in a second how that looks. And what this allows me to do is write my kernels once in a way that I can run it in both CUDA and in SYCL, and to also run it on the CPU, because I didn't want to, for each new hardware or each different manufacturer, each different language, I didn't want to rewrite the whole simulation. So I can maybe just show you a little bit in the code how this works. I don't know if this is too small, but this is an example of how one of these functors works. It's just a C++ class that you define with, you can think of all of the member fields of this class. These are your input arguments of your function, if you think of your class as a function. And then for this object, you define the operator paren, with one input variable, which is an index, which tells you which position on the grid you're currently dealing with in this thread. And the idea is over your whole grid, you give it this functor, you launch it on a device, and it spawns all of these threads that are going to solve all the different positions on the grid. And once you define an object like this, I just have different wrappers that actually, as a zero cost abstraction, will run this in CUDA as a CUDA kernel, or in SYCL in a SYCL parallel for loop, or in OpenMP on a CPU as a OpenMP parallel for loop. So I can just write this once, and the same code is used on all of these different types of hardware. Which allowed me to do this as a project that as many people as possible are able to use, because that was one of the goals. I didn't want to be tied to a given hardware vendor for any of this stuff. So what do I get back out of this is that it makes it a lot easier to share results. I get all of these bug reports, nice interactions with the community. So there are some downsides. The main thing is, once I tell people, hey, why don't you use my simulation? They're like, I don't want to compile things myself. I just want to download something and run it. And it turns out now, like, the Linux version is the easiest one to use. If you're giving compiled code out, you might find, if you have an open source project, that this is actually getting more difficult as a function of time. Microsoft and especially Apple are enforcing what's called code signing, which in principle is a good idea. It gives you some cryptographic signature to know, okay, has this code been modified or not? The problem is who controls the signing certificates. Especially Apple will only accept their own certificates, and the only way to do this is to pay them a yearly subscription, which is kind of annoying, especially if you're just trying to give out your code for free. Now, trying to make something fairly general, there is always more ideas than there is time to implement them. And of course, once you make something, you have to maintain it. And things break, not just by me. I break things myself all the time, but then I can fix them easily. But sometimes operating systems break things too, and then you have to go back and fix them. So it's a bit of a commitment. And then when I add features, I have to make sure that I'm not breaking other people's work at the same time. So that can lead to a bit of frustration, but in the end, I found it to be worth it. And I thought, I'm not sure how much time I have, but I could show just a simple example of how it works. So this is the main simulation here. I'm worried that it's a little bit small on your screen, but this is an example of solving. This is an optical parametric amplifier. This is something that we use quite a lot. So you can see there's a lot of colorful things happening on this plot, and for me, visual feedback is very important. And especially, for example, if I want to change one of these parameters, say the pump pulse energy of the OPA, I can do this, and then in the results, I can just move around this slider and see how things change as I change the pump pulse. You can see how this thing is saturating and all of that, and it gives sort of visual feedback of how the modes of this OPA are going to work. Now, there isn't enough time to give a full tutorial of it on how all of this works, but I want to give one example of how things can go wrong. So I have a student who actually just finished his master's thesis, and he was using my code, and he was very perplexed by some results that he was getting. And I mean, he knew that, okay, it's a numerical simulation. I have to look for convergence. And often you look for convergence versus like your different step sizes. You make the step size smaller. based on the order. Most of the things in here are fourth order, so they just kind of snap into place once you get a good parameter range. But he didn't think to check not the step size, but the grid size. And in this sort of configurations, let's see if I make my grid size half as big, you can see something absolutely crazy is going on here. And this is because the light is hitting the grid in a way that you might not be expecting. I actually have a periodic boundary, and now light is showing up where it physically can't. And in this situation, it's kind of obvious, but in other situations, it's not. So this is one of the dangers with releasing code to the public is I know the limitations, I know the assumptions, but other people might not. And this is always one of the things why I try to make good tutorials on how to use the code, because I mean it makes me look bad too, right? If crazy results are coming out. So I'm trying to avoid crazy results, but I mean, you find when you release your code to the public that they find all of the little corners of the crazy results that you weren't expecting to find. So that's what one of the challenges you have to deal with. All right, and before I wrap up, I just wanted to say, in addition to the nonlinear optics code, we have to, we are not just theorists. We're mostly an experimental group, actually. So we do a lot of data processing. We do this mostly in Python, and we're now just starting to make this all public as well. So if you want to use any of our data processing stuff, we actually put it in the PyPI, so you can just pip install AttoWorld to get my data processing code there. There's some useful things in there, at least I think so. It's mostly written in Python. Actually, my preferred language is Rust. I actually don't like Python that much. I don't like C++ that much either, but I have to use it for talking to GPUs. But for most of the other stuff that I do, I write it in Rust if it has to be fast. So this library is a Python library, but with anything that needs to be fast is written in Rust, but you can call it from Python, including frog reconstruction if there's any ultra fast people in the audience. My frog reconstruction code is in there as well. So feel free to use that. Yeah, and so this is more recent photo of our group. The whole MPQ is quite large, but this is the group of us. Slightly outdated picture, but the group of us doing attosecond physics. All right, so that's what I wanted to cover. Let me know if you have any questions about anything, want more detail on everything, anything. I just wanted to give a sort of a overview of the stuff, and if people are curious, I can show a bit more about other parts. So thanks a lot.
Thanks a lot, Professor Karpowicz, for the very nice, impressive and inspiring talk. And now we have time for maybe one or two questions in order to stay on time. We have a question from the audience concerning the GPU implementation, and it's about why not abstraction library like Alpaca implementing for the GPU implementation.
Okay, yeah. So there are some abstraction libraries. Actually, the way that I do it, it ended up being quite similar to how another one called Cocos does it. I just sort of did it organically myself. So I started writing in CUDA, and then I decided, okay, I want to write it on another thing. And it's like, okay, I just came up with my own abstractions to just sort of preserve my own code. If I was starting over from scratch, I probably would have used an abstraction library. But actually, once you get in the habit of expressing your kernels as functors, which is also what Cocos does. Using Sickle or CUDA, you just have to write a small wrapper. Like the actually, I can just show you how this looks in my code. So just for different devices, like to run one of these functors on the CPU, there is just a device launch function, which here there are some if defs and all that. So just I do it in slightly different ways on Windows and Apple and those, but in the end, you just have some template function. So for whatever type of functor you have, you just send it in. So one of these wrappers for each different device, like for example, if I want to do it in Sickle, this device launch function is quite compact. Like this is the whole thing to launch a kernel in Sickle. It's again just a C++ template. You give it the functor. I have a device class here, which is doing all of the work in the back end, but you really just call this parallel for function, which is part of the Sickle handler on the functor. So there actually isn't that much code necessary to write this yourself. And for me, sometimes it's an advantage to not have extra dependencies if I don't need them. I was never motivated to actually adopt one of the libraries because the code that I wrote myself seems to work fine, and I didn't need to. So that's basically it. But that's a good question, though.
Thank you. If we have other questions from the audience, otherwise I have a curiosity more than a question. You have implemented the simulation of nonlinear optics using unidirectional pulse propagation equation or FDTD. Have you in mind to add some type of other simulation like in frequency domain or finite element method in frequency domain, or you think that these two type of solution are enough?
So far for the situations that I've encountered, these two were enough. I have to say that there is a different simulation that we use, which is actually a open source project by one of our friends in the field, John Travers, which is actually a Julia library called, or a Julia program called Luna, which was very good for the simulations inside of optical fibers, because there you want to use a different basis than the sort of spatial basis that I use here. So far, these two have covered all of the situations that I've wanted. Now, the thing is, a lot of the physics actually isn't in solving the electrodynamics. So the electrodynamics are, well, I just want to send a pulse through a material, and if I just want to see how the pulse changes, then the unidirectional pulse propagation equation is probably enough. If I have say more complicated spatial geometry, then the FTTD is more useful. But actually the light matter interaction is always taking place in this nonlinear polarization or this current term in the Maxwell's equations. I have a collaborator in Princeton who is working on solving optical block equations coupled to FTTD. And she's working on the optical block equation solver for this. So the basic idea here is that each position in space, you're solving the block equations and allowing the electric fields to propagate in sort of a more complicated geometry inside of that. But the hope is that all of this fits within the sort of standard FTTD that's happening in the rest of the simulation, so that maybe if it's a smaller volume where you have to do this more heavy calculation, but for example, it's on a substrate and you just want to use more standard nonlinear optics for what the substrate is doing, but not to ignore the substrate effects, to solve the substrate using the normal perturbative nonlinear optics, but then do the more heavy calculation just for the smaller sample that might be on top of the substrate, and to have these integrated in one thing. But for the electrodynamics itself, so far these, I don't know, I didn't want to open up any new fronts on that side.
Okay, thank you. Now I think we can close this session. We thank again Professor Karpowicz.